calibration part of the data set and with respect to the validation part of the data set. I am expecting that the error in validation becomes larger. Why is that? It's very simple, because this is a new information that the model is not trained to deal with. Calibration is a kind of training. We feed the model with known data and we optimize, we train the model to this situation, which is represented by the calibration data set. The model gets trained to it. When we get to something the model is not trained against, a new situation, or as it is called, an out-of-sample situation, out-of-sample simulation, out-of-sample simulation, of course, the model is less precise. We understand by intuition that this problem is more relevant if the calibration data set is short. If it becomes longer, parameter values become more reliable because the model is trained against a larger number of real-world situations. If we increase the calibration data set, the model gets trained and trained to new situations. And therefore, when we test it with the new data, if the model is more trained, then the error is reduced. I'm always expecting a larger error in validation, but the amount of this additional error is directly related to the length of the calibration period, to the reliability of the estimated parameters. Of course, if the estimated parameters are reliable, I am expecting a satisfactory simulation also in validation. If I see that in validation suddenly the model gets completely wrong, it means that the calibration was not good. Okay, this is called, this technique of splitting the sample of observed data in two parts, one for calibration, one for validation. It's called split sample calibration procedure. Split sample calibration. So basically, you calibrate a model and your client asks you, okay, you prove to me that your model in calibration works well, but when I will use the model in practice with a situation that is new for the model, does your model work well or not? And then you reply by saying, look, let's try to do this. I split the sample of my observed data. I use half of the sample to calibrate, and the other half it's something that is new for the model, and I prove to you that it works well anyway. Please note, the final value of the parameters that you use for application, for design, should be estimated on the whole set of the observed data. It's absolutely nonsensical if you go to application by calibrating a model by using a split sample. The split sample just serves for validation. So basically what you do, again, I provide you this example. You estimate your model with the full sample and you give to your client the answer that he asked you to deliver. And then you tell to your client, look, if you have a question about the reliability of the model, I give you this proof of reliability. Let's try, just for the sake of making this experiment, to use only half of the data to calibrate the model and to use the other half to check it. I prove to you that the model works well in and out of sample. And then you can use your model, but with the parameters calibrated on the full sample. Is this clear? You shouldn't conclude by studying the split sample option, that at the end of the story you go to application with a model that is estimated only on half of the data. This is absolutely nonsensical. You are an engineer, you have to use all the information available in order to make your design. But for the sake of providing a proof of reliability, you can use this technique. I mentioned to you half of the sample. It doesn't matter, half, 70% for calibration, 30% for validation, 30% for calibration, 70% for validation. You have to make your choice. It depends. And also keep in mind that you can switch the situation. You can switch calibration and validation in order to provide a double proof. And you are happy if parameter values estimated in different situations, with half of the sample, with the other half of the sample, with 30% of the sample, they don't differ much. If they don't differ much, it means that you are on the right path. Because it means that the model is already well trained. And if you add information, the model doesn't change much, which is something that it's fine. And this is a series of experiments that you can make. It is extremely important that you make them. Because keep in mind that hydrological models typically count a large number of parameters, and they are estimated on a reduced sample. When you are very lucky, you have 100 years of daily data. But very often you have to estimate with 5 years. And then you have to be very careful in trying to check that uncertainty is limited. And these exercises of validation therefore become necessary. Of course, had we at disposal 1,000 years of observations, we wouldn't care about validation, because a model that is trained on 1,000 years, it's for sure trained. But if a model is trained with a short time period, we need to check. And keep in mind that the larger the number of parameters, the larger the uncertainty. We say that models with few parameters are more robust. What does it mean, robust? It means that they are not perfectly optimal, but they are not perfectly wrong. So sometimes you have to sacrifice some level of detail for the sake of obtaining a more reliable representation. Sometimes we are tempted to make the model flexible and to introduce 100 parameters. But then what happens when you go to validation? Probably it's the performances decrease with the model with a reduced number of parameters. Try to have clear in mind this. So your purpose is to get the best performances in validation, not in calibration. If you want to get the best performances in calibration, you need to make the model more flexible. But then what happens when you validate? Your purpose, again, is to get the best performances in validation. Okay, there is a long and extended literature on validation. And in particular, there is a technique that is linked here, which is called, it's just linked here, cross-validation. Please have a look at this link, because it's interesting, and this is a kind of question that I may ask you. I'm explicitly telling you. I didn't want to copy and paste from Wikipedia, because this is something that first I'm not allowed to do, and second, it was not useful. So here I just tell you, given that in general I tell you, you don't have to follow my links. In this case, please follow it. It's very easy to understand, and you just need to look at the premise, and you can stop here. What is cross-validation? Basically, is rotating validation and calibration, so I already mentioned it to you. And then, in particular, cross-validation is, in order to get the optimal chances for validation, it's basically this. Let's suppose that you have 90 years of data, like in the Po River. Why split the sample only in two parts? Let's calibrate on 89 years and keep 1 year for validation. But then rotate over the years. So you perform 90 validations by calibrating on the remaining 89 years in turn, and validation with 1 year only. This is cross-validation. and of course it's an opportunity. Okay, I think that's it for calibration and validation. And again, tomorrow, bring your PC. If you have any idea for presenting something tomorrow, just send me an email by tonight, and that's fine.